My name is Dongfang Liu from Rochester Institute of Technology. On behalf of our team, I am presenting our work titled DG-Labeler and DGL-MOTS Dataset, Boost the Autonomous Driving Perception. In this work, our task is MOTS, short for multi-object tracking and segmentation. Different from image instance segmentation, the new problem aims at simultaneous detection, segmentation, and tracking of object instances in videos. To date, MOTS studies face two critical challenges. First, the published datasets inadequately capture the real-world complexity for network training to address various driving settings. For instance, KITTI MOTS only includes a few thousand of learning examples. And the quality of KITTI MOTS is not good, as we can see the valuation data. To address this limitation, we introduce a new MOTS dataset. We collect data based on different driving scenarios and organize training data based on different settings in terms of the highway, local, parking, and residential. This figure group is the showcase of our data. The second challenge is that annotation effort. MOTS data requires the instance mask as well as the temporal tracking label across frames. So far, many attempts for semi-automated annotation have been made to reduce the annotation overhead. Aside from heavy engagement of human correction efforts, these methods generally have arduous implementations for the annotator and require multiple steps to achieve a desirable result. Moreover, their annotators cannot operate on a tracking level and only create instance masks in a single image. Our DG-Labeler explicitly models spatial relation to achieving fine-grained instance boundary. With limited human corrections, our annotation protocol can produce MOTS labels with appealing quality. Here we demonstrate the working pipeline of Depth-Granularity Module, which can help us produce fine-grained instance mask. Annotation volume is summarized in this table. We compare DGL-MOTS with BDD100K and KITTI MOTS in terms of the number of video clips, video frames, unique identities, instances, and instances per frame. In comparison, DGL-MOTS outperforms KITTI MOTS in evaluation metrics. Instance variations are represented by the instance appearance change as well as the temporal description, as shown in this figure. The left figure illuminates the distribution of squared bounding box size, while the right figure shows the distribution of tracking length per instance. This figure demonstrates that our dataset is not only more diverse in visual scale, but also longer in the temporal range for tracking. Table 2 reports the results for the cross-dataset evaluations to assess our DGL-MOTS dataset. For the same method trained on different datasets, their performance gaps stem from the quality of the dataset. Essentially, we observe two benefits of using our dataset in training over its counterparts. First, methods trained on DGL-MOTS all outperform their counterparts on all metrics. The improved performance indicates that, compared to KITTI MOTS 100K, our dataset captures more general road settings and driving scenarios in training. Second, the DGL-MOTS dataset can train methods to achieve improved performance with a shorter schedule than methods trained on KITTI and BDD100K. Thanks for listening.